Okay, let's get started. On behalf of Grid Analytics India, let us welcome each of you for the webinar on time series analysis for business forecasting. For today's webinar, along with me, myself Biswajit Nayak, along with me, Rabin Bharti, statistical consultant, and Prithapal, data science associate. They will help and support during the course of the webinar. This webinar has been presented by Grid Analytics India Private Limited, location Delhi, India. And the problem we are going to solve during this webinar, practical air travel passengers prediction problem discussed and solved. So we will be dealing with one of the air travel passengers forecasting. So what the agenda we have stored for you today? We will be covering during the webinar introduction to time series analysis and business forecasting, problem solving approach to business forecasting, problem solving using statistica, visual data science with no or low code, problem solving with collective intelligence. In these sections, in addition to these statistica, also we will approach to solve this air fabulous passenger forecasting using popular open source software like R and Python. Raw data to model deployment. So during the webinar, what we will be discussing, you can take this also as a capstone project for your further and future use. Next steps and the questions. So before getting started, let us make a disclaimer. This webinar on time series analysis for business forecasting is designed and intended solely for learning and informational purposes. The session does not constitute professional advice, certification, or job assurance. Examples, datasets, software tools, and methodologies shared are illustrative and may vary in real-world application. Participants are advised to independently validate concepts before implementation. The organizers, speakers, or associated institutions shall not be held responsible for any direct or indirect consequences arises from the use or interpretation of the information provided during the webinar. This is our third edition of public webinar. More advanced session will follow soon. This webinar is not an exhaustive training program. Rather, it is designed to provide the essential skills, foundational knowledge, how to build and win with predictive model management lifecycle and career preparedness needed to begin or enhance your journey in data science as a career destination. So let me launch this Statistica, a visual data science platform. I hope you can view my screen.
Yes, sir. Yes.
Okay. So I have launched Statistica, a visual data science platform software. So we'll be picking one of the data sets from the Statistica inbuilt example. Statistica provides 100,000 of the inbuilt data sets for self-paced learning and practicing. I am pulling a data called G series G data. You can view the volume of the data set on the top of the screen. That the volume of the data is 1P. The V denotes to the variables of the column series G and 144C. The C denotes to observation cases or the rows in the left hand side. January 1949, February 49, so and so. So what is the description of the data? In the series G column, you see 112. This is the monthly passengers of air travelers that has been recorded in thousand. So 112 described as 112,000 passengers that traveled during the month of January 1949. Likewise, this data has been recorded for 12 consecutive years, monthly wise, right? So 12 years means 144 observations we have. So what our task here, we have the historical data till 1960. So before getting started, let me get you a foundation of time series. What is the time series is all about? Time series is a statistical technique used to analyze data collected over time to identify patterns, trends, and seasonal variation. It helps in understanding past behavior and forecasting future values. What is business forecasting? Business forecasting is the process of predicting future business outcomes based on historical data, right? So here in this case, we have the historical data of 12 years, 12 like with months, right? So we have the 144 observation, the monthly historical data we have, right? What is the business benefits of the business forecasting? It helps organization to plan resources, events before it happens, kind of thing, manage risks, and make strategic decisions with greater confidence. Forecasting can cover sales, demand. There are a variety of applications the forecasting can be applied in the area like sales, demand, revenue, cash flow, and customer behavior. But during the webinar, we're not covering all that technique. We will cover common forecasting methods like neural network, that is an AI approach to solve this passengers prediction problem. We'll be using ARIMA, SARIMA. This is one of the most widely used classical statistical technique for prediction or forecasting. Then we will be using the exponential smoothing. What is neural network? Neural network again is a very old aged AI technique. Neural network are computational models inspired by the human brain, right? You can say that the architecture of the neural network is the mimic to the human brain, designed to recognize patterns and learn from data. They consist of layers of interconnected nodes called neurons, where each connection has a web that adjusts during training. Neural networks are widely used in tasks such as image recognition, speech processing, time series forecasting, and natural language processing. ARIMA, SARIMA, right? The SARIMA denotes to seasonal auto-regressive integrated moving average, right? And the ARIMA denotes to auto-regressive integrated moving average. It's a time series forecasting model designed to handle data with both trends and seasonal patterns. Exponential smoothing, time series by weighting recent observation more heavily. So this is what we are going to cover during the webinar, the methods or the technique. Right? In order to prediction, Statistica provides a multiple way, multiple interface. Let's get a quick view what all the techniques are available in the Statistica in order to complete the tasks of the time series forecasting. Because what the interface you see now, this is what we say the ribbon bar, just feel, look like an Excel. If I expand the type series, these are the methods are supported by the Statistica time series methods, ARIMA, and autocorrelation functions. interrupted time series analysis, exponential smoothing and forecasting, spectral Fourier analysis, seasonal decomposition, X11 upon Y2K census to monthly, and distributed lag analysis. These are the methods that are supported by the conventional uh, uh, under the statistics tab. This is the missing data imputation, statistical support with overall mean, interpolation for adjacent points, mean and adjacent points, median and adjacent points, predicted values from linear trained regression. Not limited to, because what the technique has we describe, time series is a classical statistical technique. So you need to at least the intermediate level of understanding of statistics in order to take maximum benefit of the time series methods. But no worry, uh, I don't have a statistical background, so I will figure out what are the all alternate approach we have in order to deal with this forecasting problem. So here we have another method called neural network, which comes from the AI, artificial intelligence family of algorithm. In the Statistica neural network, it supports to solve a variety of the problem that covers regression, classification, time series regression, time series classification, cluster analysis. So here, since the data are stamped with the timestamp like January 1949 to February 49. So it falls into the category of a time series regression. So in best of the interest of the time, we are getting into a more uh, user-friendly approach where normally the Statistica will guide me the step by step how to complete my tasks of forecasting since I am a beginner without the knowledge of the statistics. So let's see how to do that. As I have been talking, we will be getting into the statistical visual data science workflow. If I click here, add to workspace, I get this visual data science workspace, right? Here, my data, the series G, my data of my interest has been activated in my workspace for further and future analysis. If I go to the node browser, I get all the methods and functions which are available in the ribbon bar and the classic menu or the tool interface. So initially, I would like to visually inspect the data, whether the data qualifies for the time series, whether the data follows a trend as well as seasonality, right? So I go to graphs. Under the graphs, we have a popular graphs called 2D line plots, or that is also popularly known as a trend graph. I double click here. I bring this graph into the statistical workspace. I will choose the variable my interest since I do have. So I will be going with the rest of the specification will remain same. I would like to have my case names in the x-axis. So let's go with the default specification. Let's run this node. So for the output, we get the two pieces of the output. One, it appears in the node itself in a book kind of symbol. If I expand that, I get my graph, right? So here I can confer the trend. Here what I can observe here, because these are an increasing trend, right? Over a period of time. And if I would like to visually inspect the seasonality, what I observe in the month of typically in the month of November, there is a decreasing trend in the passengers traveling in the airlines. So what, because this is a very, very appropriate data which qualify both the trade as well as your seasonality. And as I submitted, in order to do this, I shown you the two methods, one through the conventional time series. Alternatively, we can do through the neural network, through the ribbon bar also. In addition to that, we have another shortcut tab which is defined to solve the time series forecasting through the AI. We have a node called SAM. If I double click here, I get same time series regression what we experience in our ribbon bar. So let's connect this both the node for the analysis. I will choose the variable my input series G. Okay. Okay. I will go and define my specification here. Right. I will keep all the specification as it is. If you observe, like we have split the detail of computed results reported. What kind of the output we would like to get? Minimal comprehensive. I'll go with the comprehensive one. Missing data. Since we do not have missing data, we can skip this, or we can apply the mean substitution sampling method. By default, it gives me the random. We have another option also, sampling variable. Train sample size. So we have split this 144 data points into the 80% we have kept for the training and 20% we have kept for the testing. The network, we Statistica support the two type of widely used neural network, MLP. MLP stands for the multi-layer perceptron, very, very popular one, and convergence of the many old time neural network. Since I'm a beginner, I do not know much which of the network will work best for my purpose of prediction. I also have selected the RBF network. That is another type of popular network, stands for radial bias function. Time series, here I can define my specification here, a number of time states used as input. So we have 144. So we can define any inputs here. Number of states ahead to predict projection length. So what length I would like to, I put the 12 here. Let's go with this. These are the activation functions which works in the background in order to compute the weight or minimize the error prediction, right? So I can choose depending on my report. I can choose all this. Let's go with this specification. Let me run this node. I get the output here, right? In addition to that, I get an intermediary output also. So where I can see my prediction here, because I had chosen the only one state, so it has left from the case 2, it has taken the prediction. I had defined I wanted to do a prediction up to the 12 months. So here I see till December 1960 we have the historical data. So I had specified I wanted to have the prediction for another 12 months. So up to 156 cases I have got the prediction. If I wanted to view what are the accuracy of the prediction, in order to get a sense of the accuracy of the prediction, I can go here and I can review the documents. I can review the documents here. MLP, the MLP has worked well with one input. The one defines to the one input. There are 10 hidden layers in between in order to minimize the error and one output the prediction. My training perfection is the 95%, right? My testing perfection is the 97%. So here I can tell I have built a very, very strong model and I can claim somewhere around what I predict for the next 12 months, I can claim a 97% accuracy from the prediction. This is the error rate, and this is the training algorithm has been worked, the BMGS. This is the error function, SOS, that is sum of square. This is the hidden activation functions, that is the 10 hyperbolic, and the output activation is the ITT. Right? So now I'm very sure I get a variety of the output. Right? Here also I'm getting the same the prediction. Right? So this here I can visually also inspect the model I have built because it is very well superimposing with my historical data or the observed data. So very well visually also I can inspect. I have built a very robust and the strong predictive model. Right? I get a different statistics altogether. Right? And if I wanted to like explain my the prediction from 12 months to 24 months or 36 months, just I need to give the input and I'll get a prediction for the 24 months here. If we wanted to see the observe the data, whether visually you would like to inspect how our prediction has done well, right? So I can take the same this thing, the node. I can copy this node. I can press this. I can define my specification here. Here I do have a multiple because earlier only I was one variable. So here I do have the multiples. In addition to that, I can also make the various fitting here. Like suppose I wanted to deal with the exponential smoothing or moving average, I can do the same. Let me run this node. Yeah. So even for the 2 years, it is working well because our data are in the increasing trend. So we can see like we are getting an increasing trend of the airline air travel, the passengers traveling in the airline, right? So still 24 months also it is capturing well, right? So this is the way you can make the simulation for the future forecasting unless until it will start, it will going away or you get experience something absurd from the prediction. Okay, thank you very much. This is the from my part of the presentation, uh, an AI approach to time series analysis for business forecasting. Now I would like to invite our colleague Praveen to take over.
Yeah, thank you. Thank you, Viswajit. Uh, my name is Praveen. I'm working as a statistical consultant at Grid Analytics. And so first let me share my screen. I hope my screen is visible. Yeah. So I will do the same forecasting technique using different techniques like ARIMA models and forecasting node browser of this time series analysis. Then I will show in the Python node. This. So first we need to connect our data set. So I have already connected my data set, already imported the data set to the best interest of our time. So this is my data set. Now, I go to the ARIMA node. Before that, we need to specify our dependent variable. So from the variable tab, we can choose, actually in my data, I have taken case names and series G as a different columns. So I'm taking series G as our dependent continuous. Then OK. Then I go to the ARIMA models and forecasting node. Uh, by double clicking on the node browser, ARIMA node, we can see the parameter specifications like for the ARIMA model, we can specify our parameter like autoregressive parameter. I'm taking it as default like 0 because uh, through the autocorrelation plot and partial autocorrelation plot, we can see this autoregressive parameter P and this uh, seasonal autoregressive parameter. This will not play much role. So that's why I have chosen 0 in both the cases. And then moving average parameter, this is the regular parameter, which is 1. And this moving average seasonal parameter, I'm also taking it as 1 through the uh, through the autocorrelation function and the partial autocorrelation plot. And we can observe that as in our data set, we have observed that the seasonality occurs at the 12th month. So after every 12 months, we observe a seasonality. That's why I have taken seasonal like 12. Then we go for the transformations. Transformation because our raw series was raw series has growing trend over time and has also multiplicative seasonality. That's why we need to difference our raw series. So I have taken selecting this checkbox. Then then we we are taking first difference at like 1 for the moving average parameter, like to remove the trend, and it will pass through only one step. Then at lag 2, differencing our series for lag 2 at 12th lag, and it will pass through one step. And then we apply the natural log transformation to our raw series to remove this seasonality. Then we go for the estimation method. We have two estimation method, approximate MACLAD cells and exact ML. And we don't need this number of backcasts. So this is 0. And this is the convergence criteria. And then I go to the results tab. Under the results tab, we have 3 types like minimal result, comprehensive, and all result. I'm choosing the all results. Then level, it will plot the level with case names. So I have already selected this checkbox. And then this is the p value for highlighting the significant values. So 0.05 and white noise errors has been selected. And I am taking the number of lags at 25 to detect the seasonal patterns. And then I go to the forecasting. So this selecting this checkbox will compute ARIMA forecast, and I am forecasting the next year. I mean the next 12 months after 1960, December 1960. It will forecast the next 12 months, that is from January 1961 to December 1961. And these are the confidence limits, 0.9. And then in our data set, there is no missing values. But if the data set has the missing value, then we can impute the missing values with adjacent points through the method of interpolation. Now I'm running this node. So after running the node through the display button, now we can see the local output from this book kind of symbol. So we have this, we can see here, we have 20 outputs. So the first output is input series G. So it has the estimates of parameters. This small q1 denotes the regular moving average, and this capital QS is the seasonal moving average parameter. So both values are highlighted as their p values are less than 0.05. So both are playing significant roles. And we can see here uh, the model has been taken, ARIMA model 011 011. So this is for the a small p, a small d, a small q, and then capital P, capital D, capital P. So the first three components are the uh, regular trend component, regular series, and then the next three components are for the seasonal component. And we are observing the seasonal lag at 12, and then mean residual as 0.00142. So this means the mean square is the average squared residual error after fitting the model. This indicates that forecast errors are relatively small in proportional terms. Lower mean square directly corresponds to higher predictive accuracy. So this means here we have a large reduction in the sum of squares. A low mean square error on long scale data, which is statistically MA and seasonal MA terms. So this supports the claim that the model is accurate, well specified. Now we have, these are the covariance, correlation, and this spreadsheet shows our forecasted values. So in our historical data, we have 44 cases. So after 144, the another next 12 steps means next 12 months data. So these are the forecasted value, and these are confidence limits, lower and the upper. And then from this chart, uh, the red line indicates our forecasted values, forecasted number of passengers in the next year, and this blue line indicates the historical data, that are the observed number of passengers, and the green lines are the confidence bands. So we can see the prediction or the forecasted values are going with the same trend and increasing with the same seasonality. So you can say that it has been forecasted in the proper manner or the robust manner. And this plot shows the raw series plot. raw time series plots that are the initial plot. This is after doing the trend as after removing trend as seasonality, we get this result, the time series, only the random component. Then these are the outputs, these are the intermediate outputs. The main thing we need, the main thing we have this forecasted values, that how can we forecast with our applying the proper model specification. Now I go to the, yeah. So in this way, we can see this, how can we forecast the next 12 months or the next whatever with our own choice. But as we increase the number of forecasted steps, the accuracy will decrease. The number of cases to forecast, initially it was 12, but we can increase as a multiple of 12, or if I increase from 12 to 24, it will even forecast in the same way. Now see 4 months, that means 2 years passengers data has been forecasted. So after the next 12 years, it is also showing the same behavior. So it is forecasted in a proper manner. So now I will go to the Python node browser and I will show the same problem using this Python node browser. I have connected my dataset with Python node browser, and then I am taking, I have already written the script to save the time. No. Now I go to the code. So in the first block, I have written the code in different blocks for better understanding. So the first block is mainly for the important libraries. So I have taken the pandas, numpy, matplotlib, pandas for the data handling and numpy for the numerical calculation, and this matplotlib and C1 that will be used for the visualization. And these are from the state models library. We have imported TSA. This stands for time series analysis. So from time series analysis, I have taken imported AD Fuller, that is augmented decay Fuller, seasonal decompose, Serimax, plot, ACF plot, PACF, mean squared error, mean absolute error. These uh, libraries will be used for the time series analysis. And this is for the model evaluation like RMSE, MAE, MAPE. Now I go to this now go to the second block. Second block is mainly for the data preparation. So this extracts the active dataset series G from the active dataset and convert the text into January 1949 into date time index, and keeps only the passenger count column and renames it to the passengers. Then I go to the, so these are renaming the column passenger. So after this, I go to the third block. Third block, this will plot the original time series data. And then next, fourth block is for the time series decomposition. Original time series data into its components. So it will plot its trend, seasonality, and residual components in different graph. And then these commands will plot the components of time series. Then the fifth block is for to check the strength of seasonality, and this step two for the to these steps to use used for the ADF test to check the stationarity. Now I go to the next block, sixth block. Sixth block is mainly for sixth block. It will apply the differencing technique for to remove this trend component, and then again seasonality, again differencing to remove the seasonality. And then seventh block will plot the ACF and PACF plot to select the ARIMA model parameter. After this, I will apply the model fitting and forecasting. After choosing the ARIMA parameter through the ACF and get into the training and testing set. The the that will be our training data set. Then we fit the SARIMA model and on the decomposition and ACF and PACF analysis. After that, I will forecast my model. Then visualization and results. So mm, full timeline with forecast. So it will show the forecasted value with the full timeline. And then the next 11th block is for the residual analysis. So our residuals should be white noise and should be normally distributed. White noise means they should not be correlated within themselves. So they should be uncorrelated. So through the graph, we can visualize or we can see the residuals are white noise. Then in the 12th block, I have just forecasted and plotted the forecasted values and printing the forecasted values. And these are the summary statistics. So when we run this node, I will get when I run the node using green play button, you can see the running status through the bar below, green moving bar. So now we can go to the local output from the book kind of symbol. And we can see here, right in the left pane, we have observed we got 8 plot outputs. So in plot 1, we have the raw time series plot. That was the raw time series plot through which we can see the growing trend and the multiplicative seasonality. In the next plot, I have this decomposed component of the time series. This is the original data. This is the trend component, upward moving trend. And this is a seasonal component, which the number of passengers repeats itself. And this is the residual component, that is random in behavior. And the plot 3 is the ACF and PACF of original series. Plot 4 is the ACF and PACF for the different series after removing trend and seasonality. And this is the prediction of next 24 months. So the red line is the prediction, and this the light red portion is the confidence region. You can see through through this part the prediction. The prediction goes similar with the historical data. And this plot is for the residual analysis. Plot 7 is for the future forecast. So this is after uh, December 1960. So this is the next 12 months, that is from January 1961 to December 1961. So this is the forecasted passengers with the confidence region. So
Running
this,
out of the time, could you please
yeah,
complete a
yes,
little
sir.
earlier?
Yeah, yeah, sir. So through the output spreadsheet, we can see these all months, passengers, and the series date. And these are the statistics which we will get in the intermediate steps. And we can see that residual statistics mean is 0.29, standard deviation is 15. So these are the summary that average passengers in 1960 is 1476, forecasted average for 1961 is 555, and we can see in the passengers that is 16.6% in the year 1961. So in this way we will use this Python node browser also. So this is from my side. Thank you. Now I
Thank you,
will
Praveen.
invite, yes, sir, yes, sir will guide you. Okay.
Thank you, Praveen, for this nice presentation. Now, I would like to invite our colleague Preetha, Data Science Associate, to carry forward. Preetha, you have 20 minutes. Okay?
Yes, sir.
All
Thank
right.
you, Praveen. And thank you,
Yeah,
Biswajit,
thank you.
for giving me the opportunity. So my name is Preetha Pal. I am currently working as a data science associate at Grid Analytics India. So let us first share my screen. So we have, as of now, just seen that the air passenger data has a clear trend and the strong seasonality, and that ARIMA and the SARIMA can model it. Now, for the best interest of time, I will skip the above explanations given by Biswajit and Praveen, and I will straight show you a different forecasting philosophy called exponential smoothing. Here, exponential smoothing means is a forecasting method that assigns more weight to the recent observations and exponentially decreasing weights to the older observation. And the smoothing means reducing random fluctuations in a time series. So before getting started, let us first plot the same series G data in a time series plots. So in the general section, the plot lists of variable will be one multiple line graph and the levels plots with the case names. So case names will be attached. So this box will be checked, and if there is any missing data present in the dataset, it will replace the missing data with overall mean. And there are several other options, but for this time I am choosing with overall mean or the by default option. Next, okay. Next, if I click the node, here from the time series plot, we observe that the data is not random. It shows a clear systematic trend. There is a clear upward movement over time, meaning the average level of passenger numbers is increasing year by year. Like the number of passengers in January 1949 is lesser as compared to the January 1954. We can see every year the number of passengers is increasing. Next, we observe a repeating pattern every year where peaks and troughs occur at similar months across years. Now, if we keep the mouse pointer here, we can we can very well see between January 49 to November 1949, in the middle of the 1 year, the peaks are high. So in the summer month, the passengers are more, and in the beginning or the end of the year, like in the month of November, the passengers is less. So this indicates a seasonality with a fixed periodic pattern. Next, if we observe seasonal fluctuations, it increases as the overall level of series increases. The height of every seasonal peaks grows over time. Means the heights of the seasonal pattern means from March 1953 to between January 1954, the peaks are different than the next 1 year. So this indicates multiplicative seasonality rather than the additive seasonality. So we can very well see from the graph that for the air passenger data, the trend and the seasonality is present. So if one is conceptually clear, she or he will very well know that when there is no trend and the seasonality present in the time series data, normally we use simple exponential smoothing, and if the only the trend component is present, we use the double exponential smoothing, and when the trend and the seasonality both are present, we use third exponential smoothing. So let's get started from simple exponential smoothing for the ease of understanding. Here the seasonal component is none. I am just taking all the by defaults option. Here trend component is also none. Here parameter alpha. Here in the trend component section, we have several other trend pattern like linear, exponential and damped trend. Here linear trend means when the series increases at a constant amount of time, and exponential trend means when the series increases by a constant growth, and damp trend means series will first grow initially, then after a certain point of time it will gradually decrease, then we use the damp trend. So for the time being we are using none because we are just showing what is simple exponential smoothing. Here parameter alpha is the leveling coefficient when the trend and seasonality are not present. Parameter delta is the double exponential smoothing coefficient. So for the analysis, I am taking it 0. Parameter gamma is the third exponential smoothing coefficient. So for the analysis for this time being, I am taking it also at 0. Number of cases to forecast, here it is 12. We can take any of it like 24 or 36, that is for the next 1 or 2 years. Next, if I click OK and if I run the node from the local report, we can first see the graph. Next, Here, if we look at the spreadsheet, we can see that for each case, like from January 1949, we have the observed series observation, and next is the after smoothing the value of the time series data. And here in the right hand side, it is residual, that is observed minus predicted value. Here smooth series means here smooth series is the value after exponential smoothing. Next, if we check, so we had initially the historical data up to December 1960. So after that, from 145 case number, that is from January 1961, the it has started predicting or forecasting, but we can see the prediction is not good. It is predicting the same value for the rest of the 12 months. Now, if we check at the summary of error from mean square, we can see that the MAC is 1403.54, which is quite large. So if you take off this as a note, we can again verify what will be the scenario for the second exponential smoothing. So for second exponential smoothing, the seasonal component will again be none. Seasonal lag will be 12 because we have 12 months for each year. Here now with the trend component will be linear, as our from our data we have seen that trend is linear in nature. Next, again the double exponential smoothing parameter and the triple exponential smoothing parameter. The double exponential smoothing parameter I will be taking again as 0.9 and keeping the third exponential smoothing parameter as 0. And again taking the number of cases to forecast as suppose 24. Next, click OK. Now if I run this node from the local output, if I see now as compared to the first simple exponential smoothing, in the double exponential smoothing mean square error has been reduced a little bit, that is 1200.60. And in the spreadsheet, if we look from again from the case number 145, we can see the scenario is little bit changed. Now the predicted value are different for each month, but again MAC is high. Now we shall verify with the third exponential smoothing. Now we will take the seasonal component as multiplicative as we have shown from the graph. Next, the simple exponential smoothing coefficient and the double exponential smoothing coefficient delta will be 0.9. And next, I am taking the third exponential smoothing parameter gamma again as 0.9. You can take any value of these three parameters from 0 to 1. These are the range of these parameters. And here again I am taking the number of cases to forecast as 12. You can take any of 12, 24, 36, etc. Up to 48 it will give robust results. Next, if I click OK, and now if I run the node again, now if we look at the mean square error or the summary of error, you can get to see the error has been reduced to 238.91, which is much lesser than the simple exponential smoothing and the double exponential smoothing. And in the exponential smoothing spreadsheet, we can see that from the case number 145, it is predicting it or it is forecasting for the next 1 year, that is for 1961. So we can from here, from this error based justification using the mean square error, we can say that the lower the mean square error indicates better fit, which confirms that third exponential smoothing is the best method for our air passenger data. Next, I can show you the same operation using the R node inside the statistical's workspace interface. For the best interest of time, I have written all the codes beforehand. So first, so I have written the first command, that is data is active dataset. We load the original passenger data from the active dataset by writing this command. Next, next from the dataset we have extracted the first column as it has only was one single column. Next, we converted the data into a monthly time series starting from January 1949. Next, we have plotted the time series. This plot will visually reveal trend and seasonality in the passenger data. Next, add grid. Here, grid lines are added to improve visual interpretation. Now, as before, we will verify each of the exponential smoothing. First, the simple exponential smoothing. For simple exponential smoothing models, only the levels of the series. Then here we extracted the smoothed values by writing the y underscore ts and I named it. Next, alpha is equal to 0.9 and beta and gamma, which are the double and the third exponential smoothing coefficients, and will not be much helpful here, so we have kept it as false. Next, in the double exponential smoothing models, since level and trend both are present, we have given the alpha is equal to 0.9 and the beta is equal to 0.9. Next, we have fitted the double exponential smoothing model. In the next line, we have computed the mean square error, which will evaluate the improvement after adding trend. Next, DES forecast, which I have written for forecasting following the estimated linear trend. Next, I have written for command for the triple exponential smoothing. Here I have, it is the the function used here is Holt Winters, and here all the three coefficients for the simple, double and the third exponential smoothing, the coefficients are taken as 0.9. Here seasonality is also added, so seasonal is equal to multiplicative, because we have seen that our data is multiplicative in nature. Next, in the same manner, I have fitted the triple exponential smoothing model, switch levels, trend and seasonality using Holt Winter. Next, I have computed the mean square error, and next it is giving the forecasted value after applying the trend and the seasonality and the triple exponential smoothing. Next, for the model comparison, we have combined all the results together. And first, we have combined all the results of mean square error, and next I have combined all the output results of all the three exponential smoothing. So next, if I run the node, by clicking the green play button and by clicking the book kind of local output button, we can get to see again we have observed a similar plot where the trend and the seasonality is visible clearly. Next, from the R console, after creating the MSc results, we can see for the simple exponential smoothing, mean square error is 1215. For the double exponential smoothing, the mean square error is more high, that is 1559. And for the triple exponential smoothing, it is much smaller than the previous two, that is 432.3259. And here is the forecasted values of each exponential smoothing. These are the forecasted value of the simple exponential smoothing, that is from 1961. This is the forecasted value of the simple exponential smoothing, that is from January, February and up to December. Again, here below is this DES forecast is the forecasted value of the double exponential smoothing method for the 1961 January to 1961 December. And next, in the below, we can see the forecasted value of triple exponential smoothing from January 1961 to December 1961. So here again, from comparing the model and comparing all the MSc results, we can conclude that as in the triple exponential smoothing, the mean square error is the smallest. So here also triple exponential smoothing gives the best results. This is from my side. Thank you.
Okay, thank you, Preeta, for this nice presentations. We'll taking all the
Thank you.
questions offline. So we had the coordinates so they can reach out because all the participants they had come through the registration form. So thank you very much each of you. And
Thank you,
for
sir.
today, we are signing out from the today session. Thank you very much.